In the previous lecture, we had an introduction to memory management, and we also had an introduction to main memory. So here, as we continue studying about main memory, here we will be discussing about the basic hardware structure in this lecture. All right, so let's see what is the basic hardware structure and what we can learn from this. So as we talk about memory, memory consists of a large array of words or bytes, each with its own addresses. So think of memory as a large array of words or bytes, which is the data that is stored in memory, and each of them will have their own addresses. So memory, you can think of it as a block, which will consist of large array of words or bytes. And how do we access this memory? We need to have some way to access this memory. And the way to access this memory location is by using their addresses. So this is a very important thing that you need to keep in mind, that all the memory location will have a specific address that is designated to it. All right. And then the CPU fetches instruction from memory according to the value of the program counter. So we know that in our memory, we are having the data stored, we are having the programs that are stored. Now, when the CPU wants to make use of some data or program that is present in the memory, what it will do, the program counter will tell the CPU where is that memory location or from where it is supposed to fetch that data. So the CPU will fetch that data or instruction from the memory according to the value of the program counter. And then these instructions may cause additional loading from and storing to specific memory addresses. So this is just a basic of how the hardware structure of memories work. So the main thing to keep in mind here is the memory addresses. Now let's see how a typical instruction execution cycle works. A typical instruction execution cycle first fetches an instruction from memory. So this is what I already explained. It is going to fetch the instruction from the memory, and the instruction is then decoded and may cause operands to be fetched from memory. After the instruction has been executed on the operands, results may be stored back in memory. All right, so let's take an example of a simple operation here. Let's say that we want to add two numbers, 2 plus 3. Now 2 and 3 are the operands. Now we know that these operands has to be stored somewhere in memory. So imagine that 2 is stored in one memory location and 3 is stored in another memory location. So if we want to add this, what will happen? We first have to fetch this 2 and 3 from their respective memory location. So we need to find the addresses of these memory locations of 2 and 3, and then they will be fetched. Now after they are fetched, it says here the instruction is decoded. This is because data is stored in memory location in different formats. And for the CPU to understand and execute them, they may have to be decoded. So that will be done. And after that is done, what will happen? The instruction will be executed. That is, the addition will be done, which is based on our example. So 2 plus 3 will be added. And what is the result? The result is 5. So after the instruction is executed, the result may be stored back to memory. So we need to store the result also to some memory location. So the addition or the sum of 2 plus 3, which is 5, that result will be stored back to some memory location again. So this is how a typical instruction execution cycle works. All right, now moving on to the basic hardware structure, the CPU can directly access only two of these memories. What are they? First one is the registers built into the processor, and then the main memory. So the CPU, which is the central processing unit of our computer, it can access directly only these two things, which is the registers and the main memory. So what are the other things that we have apart from registers and main memory? We have many things under the secondary memory, like our disk drives, which may be your hard disk or your solid state drives, and we can have the external storage devices. All this comes under secondary memory. But the CPU can directly access only the main memory and the registers, which are built directly into the processor. Now, there are machine instructions that take memory addresses as arguments, but none that take disk addresses. So the machine instructions which are used for executing operations, they will take memory addresses as arguments. So when we say memory addresses, remember that it refers to the address of the data that is present in the main memory or the registers, and it will never take disk addresses as arguments, because as I said, disk addresses. So what do we mean by disk? Whenever I say disk, please keep in mind that we are talking about the secondary memory. So it is not going to take arguments as the disk addresses, but only the memory addresses. Why? Because CPU can directly access only registers and main memory. So any instruction in execution and any data being used by the instruction must be in one of these direct access storage devices. So as I have already explained even in the previous lecture, whenever we want to execute something, that program or that data that it is going to use must be present in one of these direct access storage devices, which is either the registers or the main memory. Only then the CPU will be able to access it and execute it. So if the data are not in memory, they must be moved there before the CPU can operate on them. Okay, so if the data or the program are not present in any of these two, then it must be first moved here from wherever it is present, and only then the CPU can access it and operate on them. Okay, now the next topic that we are going to discuss is the CPU cycle time for accessing memories. So we talked about registers and main memory. These are the two devices which the CPU can directly access. Now let us see what is the time that the CPU takes for accessing these two devices. So first of all, registers. Registers are accessible within one cycle of the CPU clock. Most CPUs can decode instructions and perform simple operations on register contents at the rate of one or more operations per clock tick. So in case of registers, CPU can access the data present in the register within one cycle of the CPU clock. So we see that this is a very fast accessing speed that we have. And why is this? Because registers are directly built into the processor. So it is very easy for the CPU to access what is present in the register. It takes only one cycle of the CPU clock for accessing these registers. So we see that this is very fast. Now let's see what about the next one, which is the main memory. So for main memory, the access may take many cycles of the CPU clock to complete. In this case, the processor normally needs to stall, since it does not have the data required to complete the instruction that it is executing. So in case of main memory, unlike registers, the CPU may take many cycles to complete. That means for accessing the main memory, the CPU can take more time because there will be many cycles involved in order to access this main memory. Because main memory is something different. It is not directly built into the processor. So in this case, the processor normally need to store. Now, why do we say that the processor normally need to store? That is because let's say that we are executing a program and then there is a part of the program that is present in the main memory and the CPU is accessing that. So it takes many cycles for the CPU to access that and then it gets hold of that data. Now let's say that another part of the program which was not present in main memory is now loaded to main memory because now that is required. Now what happens? The CPU again have to go and access that. So in the first case, the CPU did not have the complete data that it needed for completing the execution. So it again goes to the main memory and tries to get that second part of data of that same program. So the CPU have to wait till it gets the complete information that is required for completing its execution. So in this case, the processor will need to store, or it will have to wait until and unless it gets the complete instruction for its execution. Now this situation is intolerable because of the frequency of memory accesses. So what is the solution for this? The remedy for this is we can add a fast memory between the CPU and the main memory. A memory buffer used to accommodate a speed differential called a cache. So this is a remedy that we have for this problem. So we have something called a cache memory, which is something that is present between the CPU and the main memory. So this cache is a very fast kind of memory, and then the things that we need will be stored in the cache memory so that the CPU can easily access and make use of the things that are present in the cache. So if a program is executing, if the part of it that is required is present in the cache memory, then what will happen? The CPU can easily access this and it can avoid the numerous memory accesses. That means it does not have to go and directly access the main memory too many times, which will lead to slowing down of the entire execution. So if the instructions and the data is present in the cache, which is a fast memory, keep in mind, then it will speed up the execution process. So cache also is a type of temporary memory, but it is a very fast memory. And remember that it is like a buffer which is present between the CPU and the main memory, which will help in speeding up the execution. Alright, so that is about the CPU cycle time for accessing different type of memories, which we discussed here, registers and main memory. And then we saw the problem and the solution using the cache. Now we'll come to the next topic, which is protection of the OS from unauthorized access. So the first problem that we saw was the time taken by CPU for accessing main memory, and we saw the remedy for this by using a cache. And now there is another problem, which is protection of the OS from unauthorized access. So we know that operating system and its data is very sensitive, and we should not allow the users to modify what is written in the operating system. Because if the users go and accidentally or deliberately modifies what is written in the operating system, it could crash the operating system or it could crash the system. So we need to protect the OS from unauthorized access. Now, how can we do this? So as I said, the operating system has to be protected from access by user processes. In addition, user processes must be protected from one another. This protection must be provided by the hardware. So as I said, operating system must be protected from access by user processes, and also we must protect user processes from accessing one another, because there may be one user process that is trying to do something and another user process should not come and interfere or modify that user process. So user processes also must be protected from each other, and this protection of the OS from unauthorized access as well as protection of user processes from one another must be provided by the hardware. So that is why we are discussing about the basic hardware here. Okay, now the question is, how can this be done? How can we accomplish this kind of protection? So in order to do this, we should ensure that each process has a separate memory space. And to do this, we need the ability to determine the range of legal addresses that the process may access, and to ensure that the process can access only these legal addresses. So in order to achieve this protection, we need to ensure that every process has a separate memory space. Now, what do we mean by memory space? So by memory space, we mean that a particular process should be able to operate or make changes only in that particular defined memory space. So we'll be defining memory spaces for each processes, and we will say that a particular process can only operate within that memory space that is defined. So here, as it says, we have to determine the range of legal addresses that the process may access, and we should ensure that the process can access only that legal addresses. So for example, if there is a process P1, we will say that process P1 should be able to access only the memory location from, let's say, 10 to 50. So only between 10 and 50, whatever addresses are there, only that will be accessible by process P1. So memory address 10 to 50 is a legal address space for process P1, and it should be able to access only that. But how can we do this? How can we implement this? For this, we use two registers called base and limit. So using these two registers, base and limit, we are going to practically implement this solution that we have just suggested. All right, so let's see what is this base and limit and how can it be used for ensuring that a process will only access whatever is present within its legal memory space. So talking about base and limit, a base and a limit register define a logical address space. Now what do we mean here? The base register holds the smallest legal physical memory address, and the limit register specifies the size of the range. So think of this as our memory space that we have. So from 0 up to 1024000. So this is the memory space that we have. And on top of it, we have the operating system. The operating system is residing in the memory space between 0 and 256000. All right. And then here we have different processes. For example, for this process, it can operate between 256000 to 300040. So this is the memory space of this process. And for this process, it is from 300040 to 420940. And so on. It is defined for each of these processes. So what is the use of this base and limit? So the base register, it holds the smallest legal physical memory address. So for example, we are talking about this process here, which I am pointing at. So for this process, the base is 300040. So the base is a register that is going to hold the smallest legal physical memory address. That means this process can start accessing from this particular memory address. So the smallest or the minimum memory address from which its legal address space starts. So that is what is stored in the base register. And then what is this limit? The limit register specifies the size of the range. So the size of the range. So what do we mean here? So here it says the limit is 120900. So that means starting from the base address, if we add this limit, then what is the memory location that we get? That is 420940. If you add these two numbers, you will be getting this number here. So that means from the base, if you add the limit, you will get the last memory location that this particular process can access. So that is what we mean by the base and the limit. So here, if the base register holds 300040 and the limit register is 120900, then the program can legally access all addresses from 300040 through 420940 inclusive. So that is what I just explained. So the base is the smallest legal address from which the legal address space starts for the process, and then limit specifies how many addresses starting from here it can access. So if we add these two, we'll get the last memory address that this process can legally address. So this is how, using base and limit, we are able to specify the legal address spaces of the particular processes. So a particular process will be able to access and operate only within its legal address space. So if this particular process tries to access memory location 0, it will not be able to access. Why? Because the legal address space for this process is only from this address up to this address. It will not be able to access any other address spaces. So the operating system is present here. It will not be able to access this directly because this is another memory space and it is not within the legal limit of this process. And also you see these are other user processes. For example, if this process tries to access or modify something for this user process or this, it will not be able to do it because, as we just said, the legal address space for this process is only from this address till this address. So here is a flowchart that describes how it works. So here, for example, there is an address that a particular process is trying to access. Now what will happen? So it will first check if this address is greater than or equal to the base address. Now we know that a process is able to access only that address space that starts from the base and goes up to base plus limit. So here, if it is greater than or equal to base, it will be able to access. We say yes. And in case if it is not greater than or equal to the base, that means if it is less than the base, what does it mean? It means that it is not within that legal address space of that process. So if it is no, we are not going to allow it to access that. So it goes to a trapped operating system monitor and it will throw an addressing error. Now let's say that the address that the process is trying to access is actually greater than or equal to the base. So it comes to the next flow here and it checks if this address is less than or equal to the base plus limit, because base address plus the limit is going to give us the last memory location that the process is allowed to legally access. So if the address is less than or equal to base plus limit, then yes, we can allow it to access the memory. If it is not, then it is not allowed and it throws the same error. So this is how the checking is done to see if we should allow a particular process to access the memory that it is trying to access or not. Okay, so the base and the limit registers can be loaded only by the operating system, which uses a special privileged instruction. So we said that we should not allow unauthorized access to the operating system. Now the base and limit registers that we have discussed just now, it can be loaded only by the operating system, and the operating system uses a special privilege instruction. And since privilege instructions can be executed only in kernel mode, and since only the operating system executes in kernel mode, only the operating system can load the base and the limit registers. So we have already discussed about kernel mode. So kernel mode is the mode in which operating systems execute. So user processes cannot execute in kernel mode. And we said that the base and limit can be loaded only by operating system which uses privilege instruction. And this privilege instruction can be executed only in kernel mode. And who can execute in kernel mode? Only the operating system can execute in kernel mode. So base and register can only be loaded by operating system and not by the user processes. So this scheme allows the operating system to change the value of the register, but prevents the user program from changing the register's contents. So by following this scheme, this will make sure that only the operating system can change the value of the user registers, and the user programs cannot deliberately or accidentally change the register's contents. So with this, we have seen how we are able to protect the OS from unauthorized access, and also how we are able to protect the user programs from mistakenly accessing each other. Alright, so with this, I hope you are clear about the basic hardware structure, and also I hope you are clear with the issues that we have discussed, and also the remedies that we have discussed for solving these issues. So I hope this lecture was clear to you. Thank you for watching, and see you in the next one.